Welcome to today's lectures. So today's lecture is van der Waal equations. So van der Waal equations, this is the equation of state for real gases. So we know that ideal gas equation equal to PV equal to nRT, and it is derived from the experimental facts of the gas laws. So gas laws, we know that the gas Boyle's law, Charles law, Avogadro law that we have discussed in the previous lectures also. Later on, so it was theoretically established by Maxwell using kinetic equations, that is PV equal to 1 by 3 m into n into u RMS square. So that we have also seen in the previous lectures. However, later on it was found experimentally that gas shows appreciable deviations from the ideal gas behavior. So what is the deviation? Deviation was that it can deviate at high pressure and low temperature. That we seen in the previous lectures. For this, go for the previous videos and study it, that we have seen it. Now, by doing all these things, Mr. van der Waal, he pointed out that the Maxwell has made two wrong assumptions in his kinetic theory of gases. So he made two wrong assumptions. So in kinetic theory of gases, there are so many assumptions in which two assumptions were false. He pointed out to faulty assumptions given by the Maxwell, and which led to wrong results. According to him, it was not advisable to assume that. So what was not that? So there are two faulty assumptions. One, two, intermolecular force of attraction between the gases molecules are negligible at all conditions. So he was not accepted this force of attraction because gases molecules do not have force of attraction, but he was not ready to accept these assumptions. Second was the volume occupied by the gaseous molecules is negligible as compared to total volume of the gas. So second point about the volume, gas says volume do not occupy any volume as compared to total volume of the gas. No, van der Waal assume that gas also have some finite mass and they also occupy volume. So we cannot neglect this point also. So he pointed out that in case of real gases molecules, they have a volume and also exert intermolecular forces. Means real gases, they have a volume, also they also exert intermolecular force of attraction. When the condition is given, when the pressure is high and temperature is low. So he applied two corrections. So he required that the gases law, the gas that we are giving, PV equal to nRT. So it requires two assumptions because gas have a volume also and gas have a force of attraction. So under conditions when the pressure is very high and temperature is very low. So we cannot take this real gas equation for the real gases for the ideal gases. So here we require some improvement in the ideal gas equation. Now, how volume was corrected? So van der Waal assumed that the molecules of a real gas are real spherical particles. Actually, gases are real rigid, not rigid spherical particles which possess a definite volume. They have a finite size. Finite volume means they have a finite size. So at high pressure, the volume of the gas is low, and the volume of the gas molecules should not be neglected as compared to the total volume of the gas. So this is the container. You can see here, this is the container in which the gas particles are there. So at high pressure, this gas volumes occupy some space over here. You can see this one. So this volume cannot be neglected. So the available free space for the molecular motion will be less than the total volume of the container. So here they are occupying some space. After occupying this space, the spaces for the molecule will be less than the total volume of the container. The space occupied by the molecule at an instant will not be available to another molecule at the same time for movement. So whenever these molecules will occupy that space, so another molecule cannot occupy that space, but that space will be occupied by that molecule only. So this was the one. So big questions. So this can be applied conditions for every molecules, that thus every molecule excludes a certain volume for other molecules. So in this way, if one molecule occupying a volume, one occupying a volume, so at that instant another molecule cannot occupy this volume. Similarly, it can happen to every molecule. So each and every molecule in the presence of the gas at high pressure will occupying some volume, and this volume cannot be replaced by the another molecule same time. So now let us consider one molecule which is at rest. Suppose we are assuming one molecule volume of one molecule at rest. Then Van der Waal pointed out that the other molecules which are in motion that excluded 4 times of its volume at rest. So what is the meaning of exclude? Exclude means there are two molecules. So there are two molecules which is occupying, suppose after the collision they are occupying some space, but that space is the 4 times of the volume of the molecule which is occupying at rest position. How this particle they are occupying the 4 times of the volume in motions. So let us see through this numerical, then we will understand. So this is the numerical of the derivation of the excluded volume. So let us assume two molecules. These are the two molecules. So after the collision, one molecule is at rest. So this molecule is rest, and one molecule which is in motion, which is motion. So this molecule is in motion, this molecule is rest. Okay, so this molecule in motion, this molecule is rest, and this is occupying. So suppose this is occupying these spaces. It can occupy here also, 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 it can occupy here also. So this molecule is occupying everywhere, and in that position other molecule cannot occupy these spaces. So how much spaces is occupied by this molecule? So let us see this derivation. Let us assume two molecules of effective volume radius r. So this is r, all are rigid spherical molecules. If these two molecules collide, the closest distance between them is 2r. So this is the 2r distance. So at this instant, the radius of the pointed circle having its radius 2r will not be available for colliding the molecules, and this pointed circle represents it. So this volume, okay, at one time to occupying this space only, but it can occupy here also, here also, here also, if it is leaving this position then. Okay, so it occupy anywhere space. So this whole spaces is called as excluded volume of this molecule. So likewise every molecule is occupying some excluded volume. So this is for the one molecule. So one molecule is how much leaving this volume. So this is leaving this much volume, okay, which is not occupied by the any other molecule. So this volume is very important. This volume is which is not present in ideal gas, but it is present in real gases under high pressure and temperature. So excluded volume for two molecules. Suppose this molecule occupying this much volume and this molecule occupying again this much volume. So for two molecules will be again 4 by 3 pi, and distance will be your 2r. 2r will be your 4 by pi, 2r, one volume full is there, 2 pi and 2r whole cube. So this is the radius. So two molecules, this is there, 4 pi r, total volume will be 8 by 3 pi r cube. This is for the one pair of molecule. If you take the one molecule, so 8 into 4 by 3 pi r cube divided by half. So this becomes one molecule. So on dividing half, you will get answer 4 into 4 by 3 pi r cube, means 4 by 3 pi r cube is the volume of one molecule. So V into volume of one molecule in rest, that is become V, 4 into V. So V is the rest of the molecule, volume of the rest of the volume of the molecule which is in rest position. Thus excluded volume for one molecule in motion will be 4 into V. So that is the volume of the molecule in motion position. So this is the volume of the molecule in motion, this is in rest. Like this we have to assume. Now excluded or effective excluded volume of one molecule will be 4 into n into B. If you are taking n molecules of volume, this become m B. So n means Avogadro number of molecules. So B is equal to Avogadro number of molecules. Now real volume of gases, it becomes actual volume of container minus volume occupied by the n molecules in motion. So n molecule means Avogadro number of molecules. So right here V minus B, that is 1 mole of gas, and V minus NB equal to n moles of gas. So it becomes VI. VI is nothing but the real volume of gas, and B is the characteristic constant value for each gas molecule. This means that V is each gas molecules, the value of B will be different. For oxygen, B will be different. For carbon dioxide B will be different, for nitrogen B will be different. So we will see the different value, constant value of each and every gases, and its unit is liter per mole. So thus gas equation after first correction, it becomes B into V minus N into B equal to nRT, and this is for the n molecules of n moles of gas. So this is n moles, where B is the 1 mole of the volume occupied by the 1 mole of the gas molecule in the container. So this is the correction done in the volume.